So we should be going. We may need to say okay on that one.
Any lights down?
Lights down, please. All right, welcome everyone. Welcome everybody on YouTube and on Zoom. It is our second wetlands, no, water, wetlands and watershed seminar of 2024, fall 24. So thank you very much for coming to join us. So today we have Dr. Mark Rains is giving our talk, our W3 seminar. There we go. So Mark is an ecohydrologist and he has his BA in ecology, behavior and evolution and MS in forestry and a PhD in hydrologic sciences. So all the way from organismal to sort of watershed scale training and many projects sort of along that same gradient. Mark is a professor of geology at USF, the University of South Florida, and he's also chief science officer for the state of Florida for the past three and a half years. Yeah. So his research is focused on hydrological connectivity, which you'll hear a lot about today. From ridges to reefs, so from uplands all the way down to flowing water bodies and down to the sea, and how they govern ecosystem structure and function. So it's your research life, and it spans ecosystems and geographies. And your more recent science officer life, you've been charged with ensuring that science underlies sound environmental policy and protection. And I think we'll hear a little bit about how that works in Alaska, but maybe you can have questions for Mark about Florida as well. And building a shared knowledge and understanding of where the most pressing statewide environmental issues are. Is primarily focused on protecting and restoring water quality, enhancing flood resilience, and developing data and analytics strategies. So how do we actually do that with the data that we have on hand, or do we need to go collect more? Mark's been the recipient of numerous distinctions, including receiving 3 scientific and technology achievement awards from the US EPA and being elected a fellow of the Society of Wetland Sciences. Go ahead.
Thank you so much for the invitation. I really appreciate it. There's going to be a lot I cover here today. I'm going to cover about 20 years worth of research. I'm going to do that in half the time because I actually don't want to talk just about the science. I'm going to talk about what the barriers are to making that science matter and how we can overcome them and achieve outcomes. So I'm just the messenger here. There's a lot of organizations and people who are involved in this. I'm going to try as best as possible to sort of signal who they are, but first among equals that I want to point out, Kachemak Bay Natural Estuarine Research right here, and their in-state partners, the Alaska Center for Conservation Science. They are our in-state partners. Everything I talk about today is centered around them, and most of what I talk about today also involves our team at the University of South Florida. So this is Alaska, so our story is going to start, as all stories in Alaska start, with fish, and particularly salmon. So it's a iconic species, it's a keystone species, it's part of the base of a multi-billion-dollar sport and commercial fishing operation. It's also a primary protein source, especially for indigenous communities, right? So there's like no resource I know of anywhere else on the planet that's quite the same as it is with salmon in Alaska. So when we started working there, we were working in South Central Alaska. This is maybe 2005. On the Kenai Peninsula lowlands, it's the unglaciated portion of Kenai Peninsula. It's about 2,000 square kilometers, rugged and mostly roadless. And we were just interested in, I mean, salmon spend their adult life at sea, but they have to return to the streams in order to spawn. And the juveniles have to overwinter at least once. And these are mostly coho salmon, which are really ill-behaved, and they will often overwinter twice. So we're asking, where does this actually happen? So we start this electrofishing program, and we find literally, if you want to find juvenile salmon in Alaska, you look for them, right? So these green dots are places where there's electrofishing. We found salmon, and the red lines are the streams they must have traversed in order to reach those points. If there's not a green dot, we probably just didn't. Like literally, if you look, you find juvenile salmonids. The other interesting thing we noticed while wandering around that landscape is it is the leakiest landscape I've ever been. You literally can't throw a pencil without it landing in a seep or a spring. And we started thinking about, okay, so this is not just a stream problem, especially as much as we're finding these juvenile salmonids in streams that are maybe 30 centimeters wide and 5 centimeters deep. And so then we had this idea about groundwater connecting landscapes and the role that must play in supporting salmon. So we have this idea we'll call landscape support for salmon. The dashed line is our groundwater flows. The green blotches are alder patches. Alder, if you don't know, or have a symbiotic relationship with bacteria that live in the roots. They're able to fix nitrogen from the atmosphere. So that groundwater might interact with those alder patches, pick up some of that additional nitrogen, move down and interact with streamside wetlands. And that whole cocktail ends up in the stream and creates the hot spots and the hot moments that are so important for salmonid support. That was the big idea. But before we get to that big idea, I got to step back a little bit. I am a geologist and think about what do I mean by groundwater in this landscape, because it's different than ours. In the last 125,000 years, there have been at least 5 glaciations and 2 minor glacial advances. You imagine this big wall of ice comes down, the earth sinks, and it starts depositing out in front of it. It deposits these stream deposits, which are coarse grain, and then the fine grain interfluve deposits. The glacier retreats, the earth rebounds, the river's down cut into it. The next glaciation advances, it sinks it again. You get another refilling event, and it goes back and forth and back and forth, leaving behind these coarse grain deposits, which are our water bearing deposits, and the fine grain deposits in between. So fast forward to today. And this is a cross section of sort of a hillside high terrace. This is a muskeg up here, and there's the modern stream that is down cut. We got these coarse grain deposits, these old channel deposits that are maybe 3 meters in thickness, and water is infiltrating, getting into those, moving laterally, and where they outcrop on the hillside, that's where you have the seeps and springs, and that's where the water is discharging forth and ending up in the stream. So keep that in mind. We'll return to it in a little while. Well, what does this mean? Well, all kinds of things, right? So here's a spring discharging to a stream there on the left. On the right, that is a hydrograph, typical hydrograph for Alaska. There's the fall freshets over here. There's a base flow period during the cold winter months. There's peak flows associated with spring breakup. And then there's base flows again in summer. Okay, so if we query this water and ask, from whence did you come? We'll find that even here during breakup, more than 50% of that water began its journey underground. Okay? It's more so in summer when it's about 80%, and in winter when it's close on to 100%. The importance here is quite clear. These are mostly coho salmon which spawn in the fall. They have to overwinter at least once, maybe twice, meaning they have to get through at least 1, maybe 3 critical times where if there is no groundwater, there is no stream. All right, this is a really important time, that winter in particular, and it does that by temperature modulation. So here we have a plot. It's one of our team members that are standing literally on the river, so that part of the river is frozen. You can see an open water spot in the background where there is liquid water. He's about to throw minnow traps in there, and it's just going to fill them up with juvenile salmon. Right, so this is a plot now here on the right, temperature on the y-axis, and that's a full year on the x-axis. The dashed line is air temperature, that's what you expect. It's Alaska, it's warm summer, really cold in winter, -10 to -20 degrees Celsius. The solid gray and solid black lines are groundwater directly adjacent to the stream and the stream itself. This stream is about 30 centimeters wide and 5 centimeters deep. And you see that they have the same temperature, and crucially, that temperature stays above 0 year round, in spite of the fact it's getting to -10 to 20 degrees Celsius. Groundwater also plays a really important role in nutrient concentrations by providing nutrient subsidies to the stream. That's the 2,000 square kilometers plus of the Kenai Peninsula lowlands there on the left. Light gray is just no alder. The dark gray blotches are these alder patches. You can see there's dots everywhere. These dots are different field sites we have. Roughly the same watershed area, differing only in the percent cover of alder in the watershed. And on the right, you have dissolved inorganic nitrogen in the stream. And on the x-axis, you have alder cover percent cover in the catchment. And you see there's a really strong relationship. If there is no alder, we have very little nitrogen in the stream. If we have a lot of alder, there's a lot of nitrogen in the stream. Whole bunch of knock-on effects to this. And if you guys want to dig into them, we can a little bit later. Really interesting restructuring of the biota of the stream bed, all sorts of things. But the one I really want to focus on, because this is wetlands, is the streamside wetlands. Now, streamside wetlands are predominantly covered with this Calamagrostis canadensis. About 95% or so of the biomass, above ground biomass, is that grass. And so here's a couple of pictures of what that looks like. Big tabletop, I can simplify it though. We have two treatments and a control. Either the alder is very close, like just directly adjacent to the stream side wetland on the hill slope. That's alder near. Alder far is, there's some alder patch way up the hill slope, not directly adjacent, but up the hill slope on the flow path. And then the control is no alders on the hill slope at all, right? Again, most of the biomass is Calamagrostis canadensis. So if we look at the above ground biomass, it doesn't really matter if the alder's nearby or far away. They have about the same above ground biomass. But they're substantially less if there's no alder at all. We know this is a nitrogen effect because we boost them with nitrogen. And there's a modest effect here at the alder, here and alder far, but a really large effect over here at the alder. They jump up and they're all equal to one another. Well, that stuff does not stay in the stream side wetlands. Here's Calamagrostis canadensis, here's the stream. You see the Calamagrostis canadensis along the stream bank, it's dying, decaying, falling into the stream. And on the right, we see a couple of isotope plots. In both cases, the y-axis is delta N15. In the top one, the x-axis is delta carbon 13, and the bottom delta deuterium. A lot going on here, but I can simplify this one too. If we go, there we go, to these blue circles. The blue circles are the in-stream primary producers and the in-stream lower level consumers, right? So it's the stream biomass, right? The green circles are the stream side wetland primary producers, right? The Calamagrostis canadensis and the stream side wetland lower level consumers. Now, if the fish are eating one or the other, we would expect their shift in this space to be vertical on the delta N15 axis, and enrichment in N15. And the fish are right there, plotting directly above the stream side wetland lower consumers producers and lower level consumers, implying that that's where they're getting their energy from. That's where they're getting their carbon. So now let's do a big summary. Right? So here's our big conceptual model informed by 20 years of research. We've got a hill slope on the left. There's a stream over here on the right. There's groundwater moving down that hill slope. It interacts with this alder patch, which again has the symbiotic bacteria in the root that kicks nitrogen out of the atmosphere. That nitrogen-rich groundwater moves down to the stream side wetlands. It boosts above ground biomass. The groundwater bypasses a lot of that too. So there's water discharging to the stream where it augments stream flow, modulates temperatures, directly brings in nitrogen subsidies, also boosting that above ground biomass, which then falls over, serves as the base of the food chain. Beneficiaries of all this are the fish. All right, let's park the science for a minute, because that was like 20 years of work done in 15 minutes. And I want to talk about, like the entire time we kept thinking like we're doing this because we care about South Central Alaska. We want to make sure that this research matters to the people that are actually on the ground. So how do we do that? Big struggle in my entire career thinking through how that happens. So in 2019, I'm reading the Chronicle of Higher Education, and I see this sort of breathless headline, "Can University Save the World?" And a few months later in spring 2020, another one, which is Max Weber invented the crisis of the humanities. Okay, turns out both articles are about the same thing. They're about Max Weber, a guy who has a much bigger influence on our lives than we probably know. So Max Weber was, like us, an academic. He was a German academic in the late 19th, early 20th century, famous for a lot of things, sociologist. But he's most famous for an essay he writes in 1917 and publishes in 1919. So remember, 1917, Germany, it's the depths of the depravity for the German people in World War I. Go back just a few years prior to why that is. 1914, Germany starts the war with the Schlieffen Plan. The Schlieffen Plan says we're going to race to the east or the west. We're going to defeat France in 30 days. Then we're going to turn around. We're going to race back to the east. And the French allies, the Russians, will be really slow to get here because their country's really big. And then we'll defeat them in single combat. And of course, that's not how it works, right? They get bogged down in the west. They open a second front in the east. And from fall 1914 onward, they're probably going to lose the war. Only way they're going to win it is through what we call total war. Total war is you conscript your entire society at the war effort. And then you kill more people in more horrible ways for a longer period of time until your opponent societies collapse and their governments are forced to sue for peace on terms favorable to you. So they have to construct their whole society into this effort. And it's going to get grim. So the first people they come for are the academics. Two reasons, right? Number one, they're going to invent all the horrible ways to kill a lot of people over a long period of time. But more importantly, they're on the front lines of the more important battle. It's the battle for minds. They're going to convince us that this is the way we should be. And in particular, they're going to convince German youths that they should enthusiastically get out of the classroom and into a trench. Well, like all of you, Max Weber thinks this is insane. And he has a nervous breakdown. He leaves academia. It's 1917. He's allied himself with some anti-war German youths, and he writes this essay. Roughly translated, it's science as a vocation. Okay, and he makes what at the time is a very startling thesis. It's exemplified by this quote, which I'll read. If a scientist feels called upon to intervene in the struggles of worldviews and party opinions, he may do so outside, in the marketplace, in the press, and meetings and associations, yada, yada, yada. He's arguing for a firewall between the university and people. In fact, he goes so far as to argue for a firewall between university faculty in one department and another. After all, how could you be advancing the knowledge of math if your colleagues in history can understand? Right. Well, this essay, ultimately published in 1919, goes viral, like worldwide. And so we have to understand like what it finds when it lands in America. To do that, we got to go back to 1916. At least this is a good way of exemplifying it. 1916, this is where Pancho Villa comes in. He's literally a person. And Pancho Villa and his band of banditos get on horseback in northern Mexico. They ride into southern New Mexico. They pull out their 6-shooters and like pew, 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 shoot up the town. They light some buildings on fire. They steal some loot, which they put on horseback and they ride back into Mexico. 1916. And America's like, well, we got to do something. There's big debates in Congress. They ultimately get a 5,000-man army, and they give it to General John Pershing, who's about to become America's first World War I hero again, right? And we invade Mexico. And our maps are wrong, we get lost, our cars break down, our planes crash. We never make contact with the enemy, and we slink back to America totally embarrassed. Okay, 1916. So go 2 years prior, 1914, war breaks out on the continent, and we don't get involved for a couple of reasons. It's a Continental affair. It really has nothing to do with us, maybe even. We're actually not sure which side to join because, after all, there's something like 125 German language newspapers in America at the time. But more importantly, we just don't have that game. Like, that is not the game we're playing in 1914. We don't stay totally. We sell war material to both sides, actually. Increasingly, the Allies, as the shipping blockade breaks down or blocks down Germany, and the largest transfer of wealth in human history takes place. The center of world banking moves from London to New York City. 1918, we joined the war. We win some incredible battles. The Battle of Belleau Wood is still thought to be maybe the Marine Corps' finest moment. In 1919, we signed the Treaty of Versailles. And we announced on the world stage, we're a superpower. Now, we feel kind of like, well, we've always been, right? Because for us, we always have been. But we weren't. That's when it happens. 1919 is exactly when it happens, right when Max Weber's essay is going viral. I tell you that whole story to sort of contextualize this figure here. So this is on the y-axis, the number of colleges and universities in the United States. The x-axis is year. And Max Weber's essay is right there. Right when we're about to go from less than 800 colleges and universities to well over 4,000. And they're all built in the image of Max Weber's essay, with a firewall between the university and the people. We all know what that looks like, right? It's the ivory tower. This wasn't always the case, but it is today. This ivory tower over here, on one of the upper floors, we're saying smart stuff. Looks like math, so we're saying math stuff that our colleagues in history can't understand. And down below, as far as the eye can see, is why won't those scientists talk to us? And apologies to our IFAS extension fellows, we're not paid to do that. Like, it's not my job description. I get paid to get grants, so I get talks to colleagues like you, write papers, and you guys read them and cite them, right? There's no mechanism for me to talk to people. And there's no reward structure for me, right? In fact, there are strong disincentives for me to actually spend time talking to people, because then I'm not doing my other job. And if I'm interested in getting a job, getting tenured and promoted, or surviving my 5-year post-tenure review, I'm not rewarded for that historically. But things are kind of changing, right? It's like we have at USF an Office of University Community Partnerships that got puffed up about 5 or 6, 7 years ago. So they're telling us we got to do something. You guys don't have one, I don't think. It feels like you guys are sort of distributed amongst your departments, but College of Engineering has community engagement and outreach. They're telling us like, you ought to be a community engaged person. And we all know, like those of us around, like NSF, the summary page used to be all intellectual merit. Then they were like, okay, well, add a couple inches on broader impacts. Then they're like, I don't know, 50-50. Now there's whole programs at NSF that are nothing but broader impacts. So they're telling us like, you should not just be a pencil neck stuck in the ivory tower, get out and talk to the people, but they aren't teaching us how to do it, or providing us with mechanisms to do it, or providing us with formal reward structures to do it. But we're supposed to do it. So what does that mean? Well, we've all said something like this before. If only they understood they make the right decision, right? We need to educate our stakeholders. It's called the deficit model. The idea being our stakeholders have a deficit of knowledge. If we fill that deficit with true knowledge, they'll make the right choice. Okay? Plenty of research to tell us that this is total nonsense. Not even remotely how it works. It's not how people think. It's not how they behave. A lot of research tells us that what we're really looking for is we have to first establish community credibility, which has 2 important axes. The first one being, you have to have some sort of expertise, but it's not expertise necessarily the way we think of it. It's got to be contextualized by a local region, right? So it's not just that you're a smart person in Florida. It's that you're a smart person about South Central Alaska, right? So the literature calls that competence, so we'll adopt that term. The next one is trustworthiness, right? You have to perceive me as being trustworthy before you will take my information. And the literature talks about if you see me as trustworthy, you'll establish a sense of warmth towards me. So it's competence and warmth. You can ask people, how do you feel about the competency and warmth of doctors, teachers, farmers, bus drivers, and any other profession you can imagine? And if you do, you get a plot that looks something like this. So this is on a Likert scale. There's our warmth axis here, low warmth, high warmth, and here's our competence axis here, low competence to high competence. And there's this big cloud of people, of different types of stakeholders that appear within that cloud. So where do we appear? Well, a little bit of an outlier. We're seen as competent, but not particularly warm. But we're not lawyers. But neither are we, doctors and school teachers and farmers and all these really crucial stakeholders that we'd like to engage with on their terms. And in order to get there, what do? How do we move up that warmth axis from we're pretty competent but pretty cold to both competent and associatedly warm? Well, I think you can learn a lot from research into the factors in successful communication of risk to natural hazards. And so these are sort of low frequency, high magnitude events, fires, floods, earthquakes, volcanoes. You're typically an expert coming from outside to talk to a community about a community response. Like Mount St. Helens, y'all should move. Well, right? Why should I? It's been there forever. It's bulging. I can't see it. Don't you feel the ground shaking? Ground shakes all the time. How do you convince people to do something that they think is against their own best interest? I don't have the money to go to a hotel. I don't know anybody that can take me in. I don't have any money to buy food. I just this is my home, whatever. So I've replotted all the data. These are interviews. There people say all sorts of things. I've tried to put them into some sort of context that makes sense here, but you can see over here, about a third of it is that community credibility, right? About 17% of things people say are about expertise, about 17% are about trustworthiness. There's another 17% that are just like rando things people say that sort of go into this other category. I don't even really want to focus on those. I want to focus on the right-hand side. Half of them are different words that people use to say they listened, they cared, they were empathetic, they were compassionate. Half of it. And the crazy thing is that there's a ton of research to suggest that when you first meet someone, you have 30 seconds to establish this. That's it. And you can imagine why, like, you know, my ancestors walking through the woods at 3.5 million years ago with an armful of fruit, and, you know, your ancestor appears with a stick. Like, my ancestor has to make a really quick judgment. Should I invite you back to share in the bounty, or should I drop my fruit and pick up a stick? Like, we're really tuned up to making quick judgments about people. We do it all the time. When I was looking at this, I was thinking about it. I remember, oh God, like we've all seen some variant of this quote. Mine, I've chosen this from the theologian David Augsburger. Being heard is so close to being loved that for the average person, they are almost indistinguishable. People just want to be heard. If they think they have been heard, they are even more likely to make decisions, change their mind and make decisions which they think are different than what were initially in their best interests. So, what does that look like? This is where it doesn't fit with the modern vision of what an academic is supposed to do, because this takes time. So for 20 years, we've met our stakeholders at the places of their choosing, at the time of their choosing, to talk about the issues of their choosing. So this is me, I'm talking with Marcus and Bruce from the Kenai Peninsula Borough Planning Department. A borough in Alaska is the equivalent of our counties. Or talking with the Kenai Heritage Land Trust and some of their donors about peatland conservation. This is a roadside poster session we organized in association with a tour that the city was doing at some of their water resources projects. Even in the bar, like this is literally my students.
Selfie dog.
It is the dog. Okay, good for you. I mean, they're the dog. That's my student, Tyler Brino. My co-PI and wife, Kai, is taking the photograph. I'm just trying to pay. This guy's a fisherman. Oh, are you fishing? No, I'm a geologist. So what do? I look for water. 30 minutes later, we're talking about the intersections of water and fish. And crucially, talking with the native communities. This is two really big native tribal organizations, the Cook Inlet region and the Ninilchik Village Tribal Corporations. And our in-state partners, the Kachemak Bay National Estuary Research Reserve, in collaboration with the Ninilchik Village Tribal Corporation, set up this project called Ways of Knowing. We had these long conversations about what do you know, how do you know it, and crucially, what are the words you use to convey that? Trying to bring together sort of that traditional knowledge with modern scientific knowledge. So what do we hear? Well, remember it's 2005. We're just trying to figure out, like, do salmon use this landscape? And if so, where? Fast forward to today, and the conversation is substantively about groundwater. That's a central part of this conversation. Alaska, there's this idea of plenty. There's a lot of it. And we now know there's not, right? Right, we know that there's very limited water resources trapped in these sort of thin, discontinuous, old buried channel deposits. And people now understand inherently, because they've been part of this conversation for 20 years, that water comes out of seeps and springs, and that's what supports the streams and the salmonids, but also that they pay to drill by the foot, and they don't drill 1 foot beyond 4 to 6 gallons per minute coming out of their well. So they're tapping into the same aquifers and pulling that water away. It's not exactly a zero-sum game, but it's not an infinite sum game. And there's an intersection between these two things, which creates this tension between people and fish. So there's like a recursive part to this where people talk to people. Eventually they tell you something that they need. Well, we'd like to know where this happens. Where does the groundwater come out of the ground? Well, it's 2,000 square kilometers. Mostly roadless and very rugged, and I'm sure we could spend the rest of our lives having a good old time mapping these things manually, but that was a little inefficient. So we took our limited field observations, we took geologic data, and topographic data, and we used machine learning to teach our computer to find them for us. So this is the output from that. Dark blue is high probability groundwater discharge, yellow is not. It looks like a stream network on purpose, right? Because as we talked about, where are these occurring? It's where the modern rivers have down cut into those deposits and outcrop those aquifers. And so sure enough, we'll find them along those locations. When groundwater comes out of the ground, it must go into the ground. So we took a different approach. We used also the southernmost watershed here, the Anchor River as our test bed. We used multi-criterion decision analysis and analytical hierarchy process to query the literature and experts and build a model of groundwater recharge potential from very low, unlikely to occur in these white places, to very high, likely to occur in these dark blue places. This is now available to be sort of propagated into those other watersheds. So now we have something that tells us a little bit about where the water gets into the ground and where it comes out of the ground. Well, while we're doing that, City of Homer's like, this is all super interesting. City of Homer, by the way, that's like the only big city, maybe 5,000 people. And they're like, well, it's super interesting, but it's not that important to us because we drink surface water. We don't drink our water. We said, okay, so why don't we take a look at that, right? And so we did a project with them where we looked at where their water actually comes from. And so this is relative groundwater contribution to the reservoir on the y-axis in a full year on the x-axis. And you see it sort of bounces around depending upon the time of year, not a lot. Importantly, that gray line is the mean. About 55% of the reservoir water starts its journey as groundwater, and it comes out of seeps and springs, which we have mapped all around the upper watershed. So then we said, hey, by the way, you may be unaware, but we have a tool for this, right? We've already developed, we're going to punch it out. The reservoir is here and there, right? In the far left-hand side, and this is the watershed in both cases. On the left, that's the groundwater discharge potential. And the stars, the red stars, are places that we validated it to that specific location. And on the left is the groundwater recharge potential. And then we gave them the workflow. How would you use this in order to do source water protection through land acquisition and establishing conservation easements, so that we can extend the life of the reservoir before they have to build another? And of course, the thing I haven't talked about the whole time, and you've been wondering about, is climate change. And so the way it seems to be manifesting itself in South Central Alaska is through a drying trend. Kind of see it in the rainfall. I think it probably has more to do with the distribution of rainfall, the distribution of rain and snow, and also the lengthening of the growing season and the increase in the ET demand. But whatever the case, there's a multi-decadal evidence of a shrinking of water bodies and a transition from mesic peatlands to xeric woodlands. People are quite concerned because the peatlands do lots of important things, including things for our salmonids. So Kachemak Bay National Estuarine Research Reserve convenes this workshop a few years ago, where we bring a bunch of academics together with the Kenai Heritage Land Trust. They're interested in land acquisition and conservation. The representatives from both of the tribal organizations, the Creek Inlet region and the Nilchik Village tribal organizations, or at least community members from them. And we talked about, well, could you affect hydrologic restoration in order to stop the loss of peat, stop the loss of carbon, right? And could you sell those carbon credits on the carbon market and use the proceeds to do more hydrologic restoration, right? So sort of an integrated ecological and economic cycle. And so that's where we're going now. We're just starting in on this. We're talking about beaver restoration. Now, the beaver aren't there because they've been extirpated because they're recreational trapped. That would require a whole policy change and then a cultural change. So we also have beaver analog dam construction, and we're looking at what are the effects on the hydrology and what are the effects on carbon, both in the soils and the exchange of carbon gas between the soils and the atmosphere. Just a year in, so I'm not even going to bother showing you any data. In fact, the construction of this beaver dam analog just completed, and I'm going to go see them in a couple of days. So that's where we are today. I promised you at the start we're going to do outcomes, and all I told you was like, what are the barriers to get your science done, and how do you talk to people and get them to fund their science? Wasn't the point, right? The point is there are outcomes, and there's dozens upon dozens upon dozens upon dozens. I'm just going to exemplify that with a few. So remember that plot of warmth by competence? The federal scientists and state scientists plots towards 0, 0. That's not the authority. It's the borough that's the authority. They're the authority about both the science and the people and how you can craft policies that work for them. So Kachemak Bay National Estuarine Research Reserve worked with the borough to create a task force, academics, nonprofits, fisher persons, gravel miners, developers, all sorts of folks, and got them to sit down and think through what we know, which they know, right, because they were part of the conversation, and what they could do from an ordinance standpoint. And in 2019, they came up with a variety of ordinances specifically targeting protection of groundwater resources, especially as they relate to seeps and springs, and especially as those relate to fish and wildlife habitats. Nonprofits are involved. There's the Cook Inlet Keeper has this farming in our salmon landscape. There's this huge farm to fork initiative up there because you can imagine it's a long way to the nearest marketplace. And it's supported by funding from the NRCS. And so they've got this whole farming in our salmon landscape initiative where they go out and work with farmers. And the very first thing they want to tell them is to conserve water and limit water withdrawals because of the importance of that water to the fish. And by the way, I don't know if I said it, I had nothing to do with any of this. These are all community efforts, largely driven by Catchment Bay National Research Reserve and the partnerships they have in the community. Here's another one. Catchment Bay National Estuarine Research Reserve and the Kenai Heritage Land Trust work with the North Pacific Fishers Association, a series of workshops called Fish Need Land Too. Right, so these are people who spent their entire adult life mining a marine resource. And for many of them, never thought once about the fact that they come ashore. So this guy here is Malcolm Milne. At the time, he was the president of the North Pacific Fishers Association. He's holding an aquarium. We had just pulled these juvenile salmonid out of the stream, almost literally in his backyard. He's beaming. He'd never seen a juvenile salmonid and never thought that they were in his backyard. And these guys are so touched by it that they end up joining with Catchment or Kenai Heritage Land Trust in a series of land acquisition and conservation easement projects in crucial watersheds to the production of these little critters to become the bigger critters that they might see. And last, but certainly not least, in fact, my favorite of all was Catchment Bay National Estuarine Research Reserve holds these community council meetings, being in person, or they have them on Zoom. I'm sitting in Florida. You'll see the date I'm about to go to AGU. So I'm probably not going to be, popping in, but I'm just very interested. I get the email, I wonder what they're going to talk about this week. And I can see this one here. They're from 12:10 to 12:50. Groundwater presentation by the Homer Middle School 8th grade class. I have no idea why this is happening, who's responsible for it, or what the outcomes are. I just take heart because this information has gone viral. It's gone intergenerational. And I feel confident that the kids of today are going to be the stakeholders making the decisions of tomorrow. All right, I'm gonna wrap it up because I actually want to hear some. I've left a lot of details out. And I want to leave at least, I guess I'll leave 5 or 10 minutes for some questions. A lot of people have been involved. Some of them you may recognize. My wife in co-PI Kyranes, my best friend in co-PI Bill Kleinel, Dennis Wiggum, whole bunches of students, Tylen Brahenia. All kinds of people that we've worked with over the years. A lot of hauling scholars, Ernest B. hauling scholars from NOAA. We have one of them every summer. We have a couple here, Ashika and Aviva and many others. But first among equals is Cooey. I just want to end on sort of a sad but respectful note. Cooey, we lost her this year. She died of cancer. Is very traumatizing for all of us. Cooey was the longtime director of the Catchment Bay National Estuarine Research Reserve. Truly, quite literally, this is not even remotely controversial. Without her vision and her passion and her energy and her continued commitment, literally none of this would have ever happened, ever. But we have a whole new team on board. They're wonderful. They know the mission, and I feel really confident that we're going to be able to carry on where Cooey sadly had to leave off. And last, I'll thank the Denai and Supiat people who've been here forever. And the representatives today are the Cook Inlet Region Corporation and the Nilchik Village Tribal Corporation, who are the owners of today. Literally, we could not have done it without them, in part because of the knowledge they conveyed, and in part because they own a lot of the land and own most of our field sites. So we really appreciate the partnership we've had with them over the years. I will end it there. Awesome. With time for some questions.
All right, thank you. All right, thank you so much, Mark. That was really excellent, and I've never been more rapt about the history of 1910s before, so I hope that was surprising but interesting for everyone. All right, so we'll start with questions from the room, and I'll check on the YouTube and see what we've got over there. And we like to start with a student question because the professors often, we butt in. So from the room, questions for Dr. Rains.
Okay, then I'll start. We actually have two questions. This is I don't have like a big groundwater background. Can you like quickly talk about how relative groundwater contribution is like accumulated?
Yeah. So, when groundwater comes out of the ground, it immediately stops being groundwater, right? They're like, what does that even mean? Isn't it now surface water? And it's to some degree, that's true. Like it comes out of the ground, it quickly starts equilibrating with the atmosphere in terms of its temperature, its dissolved oxygen, and so on and so forth. But there's some things it retains. It retains the concentrations of some conservative ions. So in particular, in our case, I've done a lot of work to show that calcium and strontium are really good tracers. That water cannot pick up calcium or strontium, certainly in the atmosphere, and very little as it runs quickly over the top of the ground. It's got to get underground, it's got to have contact time, and that contact time is sort of, or the concentrations are proportional to contact time. If it's underground for just a little bit of time, it's got one concentration. If it's been underground for a long period of time, it's got a longer concentration. So we can start telling the difference between water that fell out of the sky and ran off versus water that's underground by looking at those naturally occurring tracers.
Nice.
So the whole idea behind the glacial melt is that as they're receding, as they move, it's allowing more of those nitrogen fixing plants, wasn't it?
The alder?
Yes, the alder to grow, which is fixing the nitrogen, and then more of that is making its way into the surface water for these primary producers, and then goes up the food chain to salmon. So, I see that whole relationship, but as you mentioned climate change, and as the glaciers continue to recede, there's a whole idea then that you now have more alder growing across the landscape, more nitrogen being fixed, allowing for more primary productivity and then more salmon. Is there a link there?
Little more complicated than that, because it turns out there's like a sawfly, I think is what they call it. There's a pest that loves alder and like hates everything else. And so there's proliferation of alder, there's also a proliferation of the sawfly, and there's a big sawfly outbreak, if I'm getting that name right. And there's actually a lot of loss. So at the same time, we're gaining it in some places, like this massive expansion of alder in some places. We also have a massive loss in others. And so we actually have a lot of questions about what's the mass balance of that. How long is that nitrogen effect extant on that hill slope that it used to have, right? That used to have an alder patch. How quickly does it start on the new patch? So there's a lot of questions there that we just haven't sorted out, and we think about, oh, let's do it. It's the right proposal. Eventually we'll get back to that one, because I think there really is some complicated stuff we have to tease out about what climate change is actually doing to the alder.
Yeah, how that affects concentration of solutes with the glacial melt, and
Yeah, there's a bunch of things I skipped over. Like I said, there's all these knock-on effects. Like it turns out, if you have higher nitrogen concentrations in the stream, the in-stream breakdown rates increase, right? So like there's certain shredders that can take in nitrogen through their gills. And so they get more robust and healthier, and so they can shred, and they can, just by virtue of there being more dissolved inorganic nitrogen in the stream. More interestingly, this study where we had there's cobbles in the bottom of these streams of some sort, right? And so we take some of those cobbles, we wrap them up in foil, we take them back to the lab, and then we look at the algal nitrogen fixation rates, and it turns out you get a reverse relationship. If you don't have much alder, therefore you don't have much dissolved inorganic nitrogen, you have really high nitrogen fixation rates by the algae. But if you have a lot of alder, and therefore you have a lot of in-stream nitrogen, then you have really low nitrogen fixation rates. So the stream biota themselves are adjusting to the nitrogen concentrations, which themselves are adjusted to the presence or absence of the alder. So very, very complicated to tease it all out.
Other questions from the room?
You have a second question?
But I did have a second question. I was gonna let him have it though. I was gonna ask like more about the relationship between like you as a scientist and like you as basically like a science communicator in a sense. Do you ever feel like there's like and as a policy informer, do you feel like there's like a big conflicts that happen often with that? Because I mean, there is like a walk you have to walk, because you do have a science background. You don't come from like a strictly only like tending to the field type of background? So what is the conflict that you feel like you have a lot when it comes to like coming from a science background and then trying to like merge
Yeah,
those worlds?
I guess I wouldn't characterize it as a conflict.
Okay,
So, I'm a firm believer in, your data tell a story, right? And so that's your main job. You're a chief storyteller of your data, and you're gonna tell a story about the world to people. And you need to tell that story in a way that's respectful of their understanding. And actually, a lot of what I talked about are things that I was told by people there.
right,
So you build this story together, and then you have a story that you all agree is sort of co-owned. We all own this story. That story creates a universe, and that universe is within which we have this broader policy conversation. Because the policy can't follow directly from the science. That would be a weird world, like if only we made all decisions based on science, right? There's economics, there's sociology, there's religion, there's politics, there's lots of reasons people make decisions. The science just sort of bounds that story you co-created creates the universe within which that conversation happens. And provides sort of a firm boundary, or at least a fuzzy boundary, where maybe we're gonna won't leave it. Maybe we're gonna leave that boundary because we have some really overriding, thing. Like there's no good scientific reason that Ukraine and Russia are fighting right now. But they're gonna fight because they have an overriding reason to do so. And we understand when we stepped outside of that boundary. So to me, that's it. And then, I do feel like there are some battles we fight, right? And I also feel like I'm 57 years old and I've won some and I've lost some. And I feel like it doesn't matter if I lose a battle. What I'm trying to do is sort of prosecute this broader war on trying to make sure that the stories that science can tell are adequately heard and considered. Again, back to this idea, we just want to be heard. If
right.
I'm heard, well, okay, make a different decision. You've heard what I had to say.
Right.
So.
So you were saying you gave some stakeholders a tool that can help them see which areas to conserve. How do you choose how far to go with that? Like you choosing, here's a highlighted map of the areas I think you should purchase and conserve versus just giving them the tool.
Yeah,
on this side?
that's it, just giving them the tool, right? So this one, right?
Yeah.
So this water, so it's this complicated, because this is the watershed that feeds the reservoir, that feeds the people of home, right? And they have their own lives and they've got their own city government and they're all making their own decisions. Inside here is a bunch of private owned land. People have homes and they've got wells. There's very little public land on the Kenai Peninsula lowlands. So you have to be doubly respectful because the city, these are their neighbors, these are them, like these are the people that they're serving. And so, they have to be careful about, they can't, first of all, they don't have enough money to buy the whole watershed, but they don't want it. Even if they could, they can't. Like, these are the people they're serving. So it's really more about providing them with the tools to sort of sequence and think about, well, where can we do sort of critical land acquisitions? A whole lot of groundwater discharge happening up here that's proximal to this high groundwater potential recharge zone. And so maybe either through land acquisitions or conservation easements on someone else's land, paid conservation easements, they can do source water protection there as opposed to somewhere else like over here, right? So, but we don't really get involved in the decision-making part of that. We provide them with the tool, we provide them with the workflow, and then we're here to answer questions, but I'm not a city manager. They've got their own battles to fight.
So that plot with the nitrogen isotopes, what was the x-axis? Do you remember when that?
Oh, yeah, so, yeah, I went through that, I was super fast. Okay. So this is delta N15, and as critters either uptake or otherwise consume nitrogen, right, which is, it's in every protein, you see it ratcheting up, right, because the heavier isotopes concentrate in the condensed phase, right, so they're sort of concentrating upwards. And there's not really an effect of the carbon-13 and the delta D. Those things, there's a much more subtle effect in those. So these are just plots to give a two-dimensional space. What we're really trying to do is separate the in-stream and stream-side wetlands on the carbon-13 and delta D plots, because these guys are getting slightly different water sources. These guys are evaporating more water than those guys. So And these guys are just have totally different pathways, right? C4 versus C3. So you get separation from of the carbon sources on the x-axis. What we're looking for is that enrichment in the nitrogen 15 on the eating axis. So what we're looking for is, do the fish plot above the in-stream sources, or do they plot above the streamside wetland resources? And it's rather surprising to us that they are disproportionately directly above those streamside wetland resources. So it's the Calamagrostis canadensis that falls in, and the bugs that fall in. Like when this was done by a guy named Steve Decker, and his advisor was Ryan King at Baylor, and they would walk around. These are overhanging banks, and they had kick nets.
Yeah.
Only they would scrape them,
Mhm.
and it would just cascading bugs would come out from the grasses, and those guys are falling in along with the vegetation, and those end up being these really important carbon sources for the fish.
And the idea of having, I get the carbon, the idea of having the hydrogen isotope on the bottom is just to confirm.
This, yeah, I could have done it with one, but I was gonna do it with two. I just wanted to do it twice. But they're both axes that we can use to separate either by a biological function or kind of source water evapotranspiration. But they're both ways to just sort of separate the stream and streamside wetlands out into two packets, and then look to see if we see a consistent response in the fish.
Awesome. Let's thank Dr. Rains again for excellent talk. Really appreciate it. So everybody in the room and everybody on YouTube and on Zoom, next week we have Dr. Alberto Canestrelli from here in the Civil and Coastal Department talking about boat wakes driving bank erosion and the loss of oyster filtration services in the estuary. So we're going to a very different setting and a different mechanism, but we'll see you next week.